Dropping a flagship processor like an Intel Core i9 or Ryzen 9 9950X into your rig essentially places a space heater directly onto your motherboard. These components now produce hundreds of watts of concentrated thermal energy in an area smaller than a coaster. If that energy isn't managed, the system triggers a thermal throttle. The processor forcefully dials back its clock speeds, causing frame rates to tank and leaving the performance you paid for sitting on the table. This heat output is categorized as TDP, or thermal design power. It's a specific wattage rating that determines exactly how much heat your cooling system must be able to dissipate to keep the hardware running at its advertised speed. This chart shows how TDP levels have climbed sharply over the last 3 years. Because heat output is reaching the physical limits of traditional silicon, your cooler now determines whether your hardware can sustain its peak performance. Navigating this market means facing a clash of extremes. On one side, brands push liquid coolers covered in LCD screens and lighting. On the other, a specialized community insists on the zero-noise, fanless industrial approach. To find the right setup, you have to ignore the visual branding and focus on the mechanical requirements of your specific components. Choosing a cooling strategy requires balancing 3 specific variables: your acoustic footprint, the long-term reliability of the parts, and your budget constraints. We start with the baseline standard: air cooling. This typically involves a high airflow mesh case and a metal tower cooler mounted directly over the CPU. Metal heat pipes draw thermal energy away from the processor and into a series of fins. From there, case fans physically push that hot air out of the chassis. Because there are no pumps or liquid loops to fail, this method provides highly reliable thermal management. It easily handles 90% of standard gaming and office workloads. It is also the most cost-effective option, because a $60 air cooler can often match the thermal performance of a $120 liquid unit. It allows you to spend more of your budget on the CPU or GPU itself. However, the physical scale of these metal towers creates issues. Large heatsinks often hang directly over the motherboard's RAM slots, making it difficult to install or replace memory sticks. This bulk also limits your case choices. Many tall air coolers simply won't fit inside modern small form factor or compact cases, as they hit the side panel before they can be secured. There is an acoustic cost as well. Under a heavy, sustained load, traditional fans must spin at high RPMs to clear the heat, which creates an audible hum. Air cooling remains the Pragmatist's choice. You trade the sleek, open look of a liquid-cooled build for a system with a lifespan measured in decades and zero maintenance anxiety. When builders push top-tier hardware to its limits, they often move to all-in-one, or AIO, liquid cooling. A schematic shows the cycle. A pump moves liquid across a cold plate to absorb heat, traveling through tubes to a radiator where fans dissipate it. Liquid transfers heat efficiently, and with a large surface area, fans spin slower and quieter. By moving the bulky cooling hardware to the edges of the case, you clear the center of the motherboard. This creates the space needed for panoramic showcase builds, where the hardware is fully visible through tempered glass. The primary trade-off is the introduction of mechanical failure points. Unlike a block of metal, an AIO relies on a motor-driven pump that is constantly in motion. Pumps have a finite lifespan, usually requiring replacement within 5 years. There is also a non-zero risk of a seal failure, which could leak liquid onto your electronics. AIOs are a calculated trade-off. You sacrifice the indefinite reliability of air cooling to gain maximum thermal headroom and a cleaner internal look. The third, more specialized path is fanless or passive cooling. These cooling systems eliminate moving parts entirely. They rely on natural convection and massive integrated case heatsinks to radiate heat directly from the components into the surrounding air. This results in a system that is completely silent, operating at a noise floor of roughly 15 decibels. Because there are no intake fans pulling in debris, these machines are immune to dust buildup. This makes them ideal for dusty industrial environments or long-term setups where regular cleaning is impossible. The drawback is the cost. Because these cases are engineered as massive thermal conductors, they often cost up to $1,000 just for the chassis. They are also difficult to build. You often need custom cold plates for your GPU, and you are forced to use components with lower power draws so the case doesn't overheat. Fanless cooling is a specialist tool. It provides total silence and immunity to dust, but it requires significant compromises in your hardware power and your budget. To decide, you have to map these cooling paths against your primary real-world constraint. If you want to build your PC, put it under your desk, and never think about it again, you are the Pragmatist. Buy a premium air cooler and a high airflow case. You accept a bulkier interior look in exchange for a reliable system that will never suffer from a pump failure. If you are running flagship components like an RTX 5090 or prioritize the look of a glass-heavy showcase, you are the Enthusiast. You accept a replacement cycle of roughly 5 years and a higher price tag. In return, you get the thermal headroom needed to prevent throttling on high-power silicon while keeping your build camera-ready. If you are building for a recording studio or an industrial environment where silence or dust protection is mandatory, you are the specialist. You accept lower power limits and a high entry cost to gain a machine with no moving parts and a near-infinite lifespan. There is no single correct cooler for every PC. The most effective build is the one that aligns your thermal strategy with your environment, your budget, and your actual needs.